center of curvature. Now, what's so important about the center of curvature? Relative to from the centroid, I repeat again, relative from the centroid, okay? Any position that is above the centroid towards the center of curvature, the y value is positive. Anywhere that is away, the y value will be what? Negative. Okay. So what's so important about this? Okay, what's so important? So we are going to address 2 points now. Okay, we're going to address 2 points. One, at point C, exactly at point C region, we call this our alpha point. And over here, we call it our beta point. So we're going to apply the formula. Okay, we're going to apply stress X is equal to minus mz over izz multiplied by y. Okay. So now watch this. Okay. So now when we look at this now, okay, we want to find sigma x at point alpha. Okay. At this stage, y is equal to y positive. Right? Y will be positive. Yes or no? Why is it going to be positive? Because it's pointing towards the center of curvature, and any point that is above, for this case, the alpha point, right? Y is what? Positive. Okay. So now when we substitute this formula, stress X alpha is equal to minus mz over izz multiplied by y positive. So when that's the case, the answer will be equal to minus mz over izzy. Okay, and it's true, right? The surface at the top is going through what? Compression. Okay, and I can also, like just now when I draw the arch, you saw something, right? Right? When I copy this, okay, I copy the top and then I paste, right? And I put towards the end, this line will not fit at all, right? So I will change the color, you can see better. If I change this to blue, okay? So this line I copy from the top, and when I move to the bottom, the length is not enough. Yes or no? Right? The length is not enough. So at the top, it's going through what? Compression. So mathematically, what you see down here, when the formula is equal to what? Minus mz over izz multiplied by y, because at point alpha, right, at point alpha, y is above the what? The centroid. So y has to be what? Positive. So the outcome of this is stress X is equal to minus mz over izz multiplied by y. So it's going through what? Compression. Okay, and it's true, it's going compression. Okay, so if I were to copy this, the curve at the bottom, okay, this is the curve at the bottom, and I'm going to change the color, and we're going to change to red, right? So this is the line that we copy from the bottom. When I put on top, it is the circumference is too high, right? So it has to go through what? Compression. So by physical observation, you can see this already. Okay. So the next one, what if now, okay, we want to find stress X.
So just one question.
Yes.
So the top surface, as you said, it's compression. So that's why we use minus mz over there.
No, the minus mz is the root formula.
Okay, okay.
This is the original form.
Oh, okay. I thought it's
The
because it's
y
compression.
is the
Yeah.
one that is changing.
Okay. Okay.
Okay?
Yeah.
So you're okay down here? Okay, if you have any question, also please ask, okay? So if we were to find stress x beta, right? Now y will be equal to what? Y negative, right? It is negative because at point beta, it is below the centroid, right? So when it's below the centroid, y is pointing away, like this arrow over here is pointing away from the center of what? Curvature. Yes or no? So when that's the case, y is equal to what? Negative, right? So when we substitute to find stress x beta, this will be equal to still minus mz over izz, right? And this will be y negative, right? So negative multiplied by negative will be what? Positive. Okay. So when it's negative, as you can see, so I'll draw the stresses. So our stresses is in what? Tension. Okay, so this is our stress x direction. This is our stress x. Okay. So when it's negative, it means it's going through compression. When it's positive, it's going through what? Tensor. Okay. So now I tend to make a lot of my own rules. As you all can see, like shearing stress, I make own rules, right? To make sure that you understand the topic. Same thing over here, I make the own rules so that you can visualize also. I want you to look at this, okay? At the head of the moment vector, okay, where I draw a circle, at the head of the moment vector is always going to be what? Compression. Yeah, not very good. Wait, my bad. I should have written more space. Okay, the head of the moment vector is always in compression. The tail end of the moment vector is always in tensor. Okay, always, as you can see from here. So I'm going to write that out. Okay, the head of moment vector is in compression. The tail of moment vector is in tensor. Okay. So I'll give you another example. Okay, I'll give you another example. Okay, so what if now I'll let you guys finish copy. Anyone, any question, please? Are you okay? I'm glad a lot of you are online, and those of you that come, I'm also glad. Okay, if in future the weather gets really bad, if you prefer to be safe, study at home. For this term, it's okay. Okay, don't force yourself to come. I will still teach online also. Yeah, and I think I'm going to carry this on even when the lockdown or whatever is over. I think it's good because yeah, sometimes we are just too busy to learn in class on a Saturday. Right, so the next thing I want you all to see is this. Okay, let's switch the direction of the curvature or the direction of the bending moment. So if we were now to have a moment acting in this way now, or the deformation pattern. So now this is our deformation pattern. Okay, that is our deformation pattern. Then I'm going to draw a centroid. So this is our centroid. So this is still our point A, our point B, as now this is our point C prime. And C prime, I'm going to have 2 points over here. I'm still calling the top one alpha and the bottom one beta, right? So I want you to observe, okay? We now know that alpha is going to be under what? Compression or tension? It's going to be longer, right? So it's going to be in tension. At point beta, it's going to go through compression. Okay, so opposite from the one above, okay? So mathematically, how is this possible, okay? So we know that now over here, the dot I'm drawing now this is known as the center of curvature. Okay, then anything pointing towards the center of curvature, now this is y is positive, going away from the center of curvature above the centroid, now y is what? Negative. Okay, so you can see y positive and y negative, right? So now we are going to find stress x. We're going to find alpha. So now for this case, alpha is equal to what? Positive or negative? Negative, right? Because it's pointing away from the what? Center of curvature. So now this is negative. So now when you find stress x at point alpha, this is equal to minus mz over izz. Y now becomes negative, right? So this will become positive mz over izz multiplied by y, and we know that it is tensile. Okay. And then you have stress x at point, we're going to find stress x at point beta. So y now is equal to what? Positive, sorry. Okay, y is positive now. So stress x at point beta is equal to minus mz over izz multiplied by y positive. So this is equal to minus mz over izz multiplied by y. So now we know it's compression. Okay. So now we apply the moment vector again. Okay, I'm going to sketch out the moment vector. By looking at the moment vector again, what can we say? The head end of the moment vector is in compression, and the tail end is in what? Tensor. Okay. So the rules that are written over here still works. The head of the moment vector is in compression. The tail of the moment vector is in tension. Okay, the head is in compression. The tail is in tension. So this is the most important thing to remember. Okay, head of the moment vector is compression. The tail end is in tension. Okay. Anyone, any questions so far? Anyone, please. Online, you're okay? Okay. Yeah, okay.
Yeah, all
Right.
good.
Yes?
All good. Thank you.
Oh, good. Okay.